Okay, hello everyone. Today's topic is center of mass. In shortened form, we say CM. You might have, maybe you already know what is center of mass. It's a common term we use sometimes in day-to-day life as well. Center of mass and center of gravity are two things that are closely related. Both are really important in physics and many scientific studies. So let's see what center of mass is. This concept is important in things like motion. If an object is moving, if a mass is moving, center of mass is important to understand the motion. Also, rotations. Rotating objects, we say that they rotate around their center of mass. Earth rotates around its center of mass axis. Moon rotates around its center of mass. Vehicles, when they move, the wheels are rotating, the axle goes through the center of mass of the wheel. So likewise, it's really important in rotations. And also, if you think about the balance of an object, think about like balancing a seesaw or a old-fashioned weighing scale. So idea of knowing where the center of mass or center of gravity is important in these kind of situations. So if you think about an object like in class we use boxes for many examples. So let's say some box looking object like maybe a drawer or a refrigerator. So this has some mass m measured in kilograms, and to find the weight for friction calculations, we mark the mass from the center, right? We mark the weight from the center and say mass times gravity is the weight. Why do we take this center point to mark the weight or to mark the mass? Why not, here's the object, why not just put it like this and say, here's mg. A person, right? He has some mass, it's distributed throughout the body, but to mark weight, we always say this is where mass times gravity. So mass is marked from some center point. Same thing here. So this location we select to represent the entire mass. This is actually the center of mass of the object. We mark this as a little point, like a point mass, but this little point represents the entire mass. This entire, if this is 50 kilograms, right, this is same as, instead of drawing the entire picture, you just mark the mass and say this is 50 times 9.81, right? So we select this point location to represent the entire mass, and that is actually the idea of center of mass. We can think of this refrigerator or the drawer as a collection of lot of point masses, right? Millions of those, and all of these are represented by this common location. There is a reason, there's a way to find that particular point. It depends on the geometry of the object. For an example, if it is a sphere, a uniform solid sphere, the center of mass will be right at the center. If it is a square, like a box kind of thing, it will be at the center. If it is a linear object, it will be at the center. If it is something not that linear, something like this, like a triangular shaped object, it will be not really the center, but more closer to the wider side, right? Intuitively, you can assume, you can make an educated guess. This is the point the mass is evenly distributed on both sides, right? If you take this point or here, this linear object, we can say the amount of mass on this side is equal to amount of mass on this side. Same thing here. If we divide along this point, the amount of mass on this side should be equal to the amount of mass on the other side. So that's the idea of center of mass. And if you want to balance something, you can use this point to suspend it or balance it, right, like this, because it has mass on each side, equal amounts. You can balance it using that point. So the idea of knowing center of mass is important for balancing purpose. Also, another important factor is in rotations. So I will try to copy a picture to show this instead of me drawing it. So let's see whether it works. So, okay. Okay, here you see a diver jumping off of a diving board, and in this case the person pretty much maintaining a straight position, and the center of mass closer to the hip area marked by a black dot. You see that the center of mass moves in a parabolic path. Now let's take a look at another picture. This time you see the person is, let me see if I can move this. Alright. Now the person, while diving, she's doing a spin, she's rotating. Again, the body rotates around the center of mass. That's the other significance of center of mass. If a solid object is rotating, you can forcefully rotate it around any point you want, but the natural rotation is around the center of mass. So the body in the second picture, you see that the body takes different shapes, like she bends her body, she stretches her body. So the center of mass also moves to different places when you change the shape of the body, but it always follows this parabolic path, right? So if a object is rotating, it rotates around the center of mass. Let's see another example. Okay, this one. So here we have what do you call this? Some tool like a spanner, I think it's called. So somebody is throwing this. It's rotating. This is like a series of pictures taken while it's moving with a rotation. So this is a translational plus rotational motion. Translational means the whole object goes in one direction. Rotational means it's rotating around itself. So the center of mass is marked by this mark red X, so plus sign. The mass evenly distributed around on either side. So when you give it a rotation, when you give it a spin, naturally it spins around the center of mass. Now, why have we give so much importance to this concept? Where's the application? So let me delete all this first. So let me pause the video for a second. Okay, so why it's important? Where's the application? Again, going back to biological studies, or in field of chemistry, rotation is very important. Exercise sciences is another field. Rotations are widely used. If you think about an athlete doing a long jump or high jump kind of sports, or pole vault, so the rotation or the location of the center of mass of the person is important to gain the maximum advantage. Right? We'll talk about these things sometime as we move forward. In chemistry, molecular rotations. Now, let's say, think about a molecule. For an example, nitrogen or N2, right? 2 nitrogen. So here we have a nitrogen molecule, and here we have another nitrogen molecule, and there's a bond between them. So these two molecules, they have mass, right? If I represent them by 2 dots, there's 2 small masses connected by some distance between them. There's some separation, there's a bond between them. So molecules have molecular rotations. They have translational motion, means they go in one direction as a whole entity, and they spin, they do rotations. So if you want to find the kinetic energy of these molecules, you can find the translational kinetic energy, you can find the rotational kinetic energy. To find the rotational energies, or to study rotations, you need to know around which point it's going to rotate. So for nitrogen, having 2 identical atoms, its center of mass is in the middle. So if this thing rotates, it rotates around this midpoint. So a rotation would look like this after some time. Now it's important to know, sometimes center of mass is not on the object, like it's not on any of these nitrogen, it's somewhere in between. Now if you think about a different example like HCl, here we have a small hydrogen and a big chlorine atom, right? 2 very different masses and connected by this bond between them. Now having 2 different masses, center of mass becomes closer to the bigger partner, the bigger mass. So the center of mass can be somewhere here, or it could be on the chlorine atom. So if this thing rotates, it rotates around this point. The rotation will be around this point. So it's kind of non-symmetric rotation. So knowing the center of mass is important in chemistry, advanced molecular studies, again, to study rotations. So there are so many applications like that. So this is why we're going to spend some time understanding how to find the center of mass in an object. Okay? Alright. So let me okay, never mind, we can keep these examples, we don't need to delete them. So we're going to talk about center of mass of a couple of different things. We will talk about discrete masses or isolated masses. Means things like this nitrogen N2 atom, or HCl, or H2O. Another example, we have oxygen and hydrogen, like this. So you see these are separate masses combined, connected by some kind of some kind of bond between them, right? And we will talk about mass distributions. Like solid objects, for an example, a piece of wood. It's a collection of distributed little masses, right? There's so many tiny little mass areas you can think about. It's evenly distributed throughout. So these distributions are difficult to study, or the math is a little difficult. Isolated masses, easy to work with. So we're gonna work with this, and maybe with the university physics class I will talk about few examples of this. This is going to be 230 stuff. Alright, so let's look at some isolated examples. Okay, so let me erase all these. Alright, so let's say we're gonna talk about HCl, hydrochloric acid. So we have hydrogen and we have this much bigger chlorine connected by, I think it's ionic bond, right? So there is some distance between them. We can call this mass A and mass B. So we can represent this by two little circles. Now when we do this representation, we're not going to draw a bigger circle for chlorine or a smaller circle for hydrogen. We're just going to draw two dots like this and call them MA and MB. We know what are the masses and the distance between them. Now you know that the center of mass will be closer to chlorine somewhere here, right? How do we find it? How do we mathematically find this? So that is what we're going to do. So what we do is we first take this this diagram of two dots and place it in x and y axis. So here's your x-axis, here's the y-axis. So we place it like this. So here's your MA, here's MB, and we need to know the distances between them. So if you measure the distance from the origin, we can call this XA distance. We can call this XB distance from the origin to this point B. And point where the center of mass, which we're going to calculate, let's call this X center of mass. So this is what we want to find out when you place this on the x-axis where the center of mass. Now you can do the same thing, like what I showed you was a very general picture. I just place it on the x-axis. I didn't have like a specific location to place it. You can always move one of the masses to the origin, so it's going to look like this, right? If you place one of those masses right by the origin, this MA going to be here, MB going to be here, and XCM is going to be here. So when we calculate XCM, we get the distance XCM, the distance from the x-axis, and it's the same distance from the mass A. Alright, so how do we find? So we'll do this later, but let's take a look at this general picture. We define XCM, distance to the center of mass on the x-axis, as the first mass times distance plus the second mass times distance divided by total mass. This is how we find the location of the center of mass. Now let's say you have some kind of molecule, a different example where, like let's say CO2, carbon dioxide. So you have oxygen, carbon, and another oxygen, right? Okay, so, and I believe it's a linear molecule like this. So that detail is not important right now. Let's say there's three masses that are in a line, straight line like this, in different distances. So MA, MB, MC. So we're going to place it on the x-axis, x and y. So here's the three masses, A, B, C, and we don't know where the center of mass is, so let's say it's going to be somewhere here, XCM. So as usual, it will be mass times distance plus mass times distance plus mass times distance over total mass, ma plus mv plus mc, or you can just say big M total. This is what you do. You add all the masses multiplied by their distances separately and divide the whole thing by the total mass. Okay, so let's try an example. Alright, let me erase all this and let me write down the equation. XCM equals MAC B plus, if there's more you can add them, divide by M total. So that's the equation. Alright, so let's think about an example. The example we have here is, I'm actually taking this example from the PowerPoints. It says there is a raft or a canoe or something, and this is 5 meters long, and its center of mass is at the middle, right in the midpoint, and length is 5 meters. Mass of this canoe is 100 kilograms, and there are 2 people in this canoe. So here's one person, he's 50 kilograms. Here's another person, he's 60 kilograms. This person is 1 meter from this end. This person is let's say 1 meter from this end. The question is, where is the center of mass of this entire thing? XCM, center of mass location. They're all in one line, right? They're all sitting on the canoe. So where is the center of mass of the entire thing? So how do we do that? So let's put the whole thing on the x-axis. I'm going to place the first guy, right, this person, right on the origin, right over here at the origin. So what are the distances? So the canoe is 5 meters long. So from here to here, 2.5 meters, right? From here to here, he's 1 meter from the edge. This guy is 1 meter from the edge. So that's 1.5 meters here. Right? So if I place this guy right at the origin, if I place him right by the origin, the mass of the canoe is 1.5 meters from that. So this is, let's say B, this is A. So A is 50, B is 100, XA is 0. We place it right on the origin, so that distance becomes 0. XB is 1.5. So the third person is 1 meter from the other end. So that means this is also 2.5. So 1 meter, so this is also 1.5, right? It's kind of symmetric distances. So the third person is over here. C is 60. XC is what? This is 1.5. This is 1.5. 3 meters. So now we have the distances, we have the masses, so we can plug this into the equation. X center of mass. where is it gonna be. So I'm just gonna assume that it's somewhere here. It could be on the other side also, we don't know. Let's find it out. XCM is MA XA plus MB XB plus MC XC over mass total. MA plus MB plus MC. The first term becomes 0 because XA is 0, right? 0 plus MB 100 times 1.5 MC 60 times 3 over total mass 50 plus 100 plus 60. So we have 150 plus 180 over 210. Yes. Y 210. So can take care of this. They all divisible by 3. So 7, 5, 6, 7, 4, 5, something like this. I'm gonna need the calculator. It's too early for me to do this without it. So 11 divided by 7, 1.57, 1.57 meters. That's the distance of XCM. This point is 1.5 centimeters from A. From A. So from this person, the center of mass is 1.57 meters to the other side, right? So somewhere here. So that's the idea. This is how we're gonna find out. This is how we're gonna find where the center of mass is. Now, if you're balancing this canoe, right, we know that its mass right here, so we might want to move them around a little bit so that the center of mass of the whole thing kind of aligns with canoe center of mass. That's better. That's better for stability, right? This is how we balance things. I mean, we don't do math. We just by guessing we can move people around and do all these things. But if you ever want to calculate, this is a way to do that. Okay, so the idea is you look at the mass distribution, measure all the distances, place them on x-axis, and then do this. Alright, so that's the first part. So the example we just discussed, it's the center of mass in one dimension, right? 1D. So it could be two or more masses, so it could be 4. They all are in one line, so you can place the whole thing on x-axis and do the math. It can be 2-3 masses in a line like this. They are all in the y-axis. So in this case we look for here we find x center of mass. In this one we can calculate y center of mass. So the math is still same. You do MA YA, like what is the distance from the origin to the point along the y-axis. So you take the whole thing, x and y, and you place these masses on the y-axis, right? If the mass distribution is vertical like this, you put them on the y-axis and then measure these distances, right? YA, YB, and YC, like that. YA plus M BYB, or if there's more you add them, and then M total. What if you have a mass distribution which is two-dimensional? For an example, think about H2O. There's the oxygen in the middle, the bigger molecule, and then you have this hydrogen, you have this other hydrogen. They are not in the same straight line, right? They create an angle between them. I believe you learn all these things in chemistry, like why it's not straight, why it's, I don't remember the word, polarized or something. Never mind. I'm not going to go into chemistry. Anyways, it's not in the straight line, right? So this is an example for a two-dimensional mass distribution. So we can represent this as here Ma with some distance here Mb, the oxygen molecule, some distance here Mc, the other hydrogen molecule. So where's the center of mass? Oxygen being much heavier, it will be more closer along this line, it will be more closer to this one, along this line it will be more closer over here, and there's two separate center of masses, the combined one will be right in the middle. So this is your center of mass, so we can say it's the XCM YCM point, right? In a 2D object, the center of mass has two coordinates, x distance and the y distance. So let's try a simple math problem. Let's say we have three masses, so I'm gonna just put them on the xy axis itself. So y and x. Let's say I'm going to place the mass A here, mass B over here, and we'll place C over here. And let's say this is MA is 2 kg, MB is 3 kg, MC is 4 kilograms. And let's look for the distances. Let's say this B is 5 meters. Alright, let's say C is 3 meters this way and 2 meters up. Right, this way it's 2 meter mark, over here it's 3 meter mark, this is 5 meter mark. Alright, now center of mass, we have to find XCM separately and YCM separately. X center of mass, so we do MA XA plus MB XB, all that, divided by the total mass. So if you plug the numbers, XA, it is at the origin, we place it at the origin, so that becomes 0. MB XB, so 3 times 5. MC XC, 4 times XC, it's 3 meters on the x-axis, right, 2 meters on the y-axis. We don't need this distance, what we need is the distance along the axis. So 3 divided by the total mass is 9 kilograms, right? 2 plus 3 is 5, 5 plus 4 is 9. So we have 15 plus 12, which is 27, divided by 9, which is 3. Yeah. Alright, YCM. So MAYA plus MBYB, all that, MBYB plus divided by the total mass, so which is, again, since we put A right by the origin, the distance becomes 0, so the first term becomes 0. That's a good way to reduce amount of calculations. Place at least one mass right on the origin. All right, MB, B is 3 kilograms. That distance, the y distance, it is on the x-axis, so y distance is, that is also 0. Right, for B there is no y distance, that's also 0. Plus C, we have 4 kilograms, 2 meters along the axis, right? 4 times 2 over total mass, again 9. So we have, this is also whole thing 0, so 8 over 9. 8 over 9 is 0.8 something. So 0.89, something like that. Let's see. 8 divided by 9 is 0.888. So the center of mass x, y coordinates, we have 3 and 0.89. That means 3 on the x-axis, 0.89, it's like somewhere here. So for this system of 3 masses, center of mass is not on any of them, it's somewhere in between. Alright, so this is the center of mass. 3 and 0.89. There are many examples like this. Molecular compounds, a good example, center of mass. So if this whole thing rotates, this compound, if this molecule is rotating, like for an example this H2O rotates around some point like this, that's the rotational point. Even in solid objects, like mostly like L-shaped objects, center of mass could be outside the object. A boomerang is a good example, or a donut shaped object like a wheel, right? Mass is distributed around this outer area, so the center of mass will be at the middle. Okay, so this is about this is how we find center of mass. I will post some example problems. We'll go over a few more examples in class, but these are the basics. Now we're not going to go into 3D, but you know, if we have a 3D object, it will be the third one, x, y, z, zm, right? You do the same thing, ma, za plus mb, zb plus, and then divide the whole thing by total mass. Alright, so that's center of mass. Thanks.